Okay, welcome again. So finally we are left with the last elementary signal that we'll be discussing, and perhaps the most important elementary signal that we will be using a lot in this course. And the signal of the function is known as the impulse, right? Now it is slightly tricky, especially in the continuous domain. So what I will do, I will first start defining this equation in the what you call discrete time domain, right? So in the discrete time domain, it's pretty straightforward. So we'll probably start with this, that the discrete time description of an impulse signal it is represented as delta of n. It is given as delta of n is equivalent to 1 for n is equivalent to 0, and for all the other points it is equivalent to 0, right? So if you plot it, it will be pretty straightforward. Let me just try to plot it. This will be my amplitude axis, time axis. So there will be only one point of interest. That will be this, when n has a value of 0. At this point, my signal value will be 1. For all the other points, 1, 2, 3, so on, as well as on the negative axis, its value is 0. Right? So it has only one sample where it has some amplitude value. So this is pretty straightforward in discrete time domain. But when we look at the counterpart definition, how we define an impulse signal in the what you call the continuous time domain, let me first write the description. So the continuous time version, in continuous time, unit impulse is defined by a pair of equations. It has to satisfy two mathematical expressions. First, delta t must be 0 for all t is not equivalent to 0. Let's call it 1. Right? Now, if you take only this description, if it would have been a complementary thing as in the discrete time domain, then we should have only this equation. Like in the discrete time case, delta n is a value of 1 for n is equal to 0, and it has a value of 0 for n not equal to 0. So on the same line, if we have discussed defined the unit impulse in the continuous time version as delta t is equal to 1 for t is equal to 0 and delta t is equal to 0 for t not equal to 0, then there would have been no difference between the continuous time and the discrete time version. Discrete time, maybe it is defined only for one point, and then continuous, had that been the definition, it would have been defined only at one point. But there has to be a difference, because you can't define a continuous time signal only at a single point. It has to span some time interval. So to conceptualize that thing, we have basically a pair of relations that your unit impulse must satisfy. First is this, that it should have a value of 0 for time not equivalent to 0, and then it should also follow this relation that if you sum up this continuous time impulse function over the entire time range, its integral should be equivalent to 1. So this kind of provides us a mathematical description. Now equation 1, it demands that the impulse function delta t, it is 0 everywhere except at the origin. Fine, because t is not equal to 0, it covers the entire time axis except for the origin. And equation 2 says that the total area under the unit impulse, it has to be unity. Fine. Now, like I said, it is a slightly complex to visualize like this. Fine. So what we do is that to graphically visualize this function, we always, first is this, obviously when you do mathematical analysis, your impulse function in continuous domain, it must satisfy these two equations. But to visualize it, to graphically visualize it like this thing, what we do is we view, so let me write it down here graphically. Delta t is viewed as a limiting case of a rectangular pulse function, as signal, whatever you want to call it, of having a unit area. Right? So just try to understand this point. I will draw a pulse signal. Okay, so this is my time axis and this is a pulse function. Let's call it, sometimes we call it a gating function, so let's denote it by GTT. And on this basis we tend to define our what you call a unit impulse function. So how do we define it? We define it like this, that delta t is the limiting case as time period tends to 0, like this. Now here is my gating pulse. It spans from minus t by 2 to t by 2, which means this span, this time period, it is equivalent to t, and this जो इसका height है आप कह सकते हैं इस pulse का, it is 1 upon t. Now if you try to find the area under this curve, under this pulse, it will be t into 1 by t, which is equivalent to unity. So this has a unit area. So it kind of fits this property. But we also have to ensure that t tends to 0. Fine. So the way we visualize it, we tend to, like I will show you here, visualize like this, that we tend to reduce this. In other words, we can say we try to reduce the width of the pulse. Like this. So as you can see, I'm trying to reduce the width of the pulse. That is, I'm tending t to 0. First it was this much, then in the second case it is this much, then this much, then this much, and simultaneously the height of the pulse also increases. This is 1 by t, then in the second case this again is 1 by t, then again this is 1 by t. Okay. So what I am doing, the duration of the pulse, I am tending it to 0, so it is decreased, and simultaneously its amplitude is increased in such a way that under all circumstances the area under the pulse it is maintained constant in unity. Okay, so this is one way of visualizing it, that it is a rectangular pulse. We go on decreasing the width of the pulse, and simultaneously the height of the pulse increases, so that the area under this pulse, I can say the rectangular in this function, rectangular pulse function, it is always equal to unity. So when we approach this limit, as time time period t tends to 0, we will have our impulse function. And the way we represent it graphically is something like this. This is my t, and delta t graphically is expressed like this. Fine. So what this representation means, it has a value only at what you call at the origin, and the total area under this curve is 1. So this is not a single sample like this. Yahan pe it's well defined, it is a single sample value at 0 having a value of 1. But here this basically represents two things. First, it doesn't have any value at outside the origin, and second, it is basically visualized as a rectangular gate function, rectangular pulse having a width of t and a height of 1 by t, so that the area is 1 and the width of the pulse, that is t, it tends to 0, which obviously means that the height of the pulse, since it is 1 by t, it tends to infinity. Fine. But again, it's not a clear cut. I mean, we have introduced these things for ease in the mathematical analysis, but physically speaking, it's very difficult to kind of define a source which can generate an impulse function, because it typically means, if you're talking about, first of all, in real world we only have continuous time signal, so we can't expect this kind of a signal in the real world, the physical processes that go around us. So it has to be in the continuous time case. But even in the continuous time case, it basically means that you have to generate a signal which has infinite amplitude, and it only lasts for literally for time t is equivalent to 0. But that's not possible. Because you talk about real world phenomena, even if there's a large blast which abruptly something bursts, it will span for some time. Right? So we kind of approximate it. For example, if a large thud is there, a large blast is there, it will have a high amplitude, right? And it will be for some time instant. So you can approximate that with the impulse function. But as far as mathematical analysis is concerned, we visualize this as a limiting function of a rectangular pulse function, which means delta t is 0 for all t not equal to 0, and the total area under this curve, under all circumstances, it has to be unity. Fine. Now it has very interesting properties. In fact, when we will start analyzing the systems, we will be first analyzing in terms of this what you call impulse function. Now first property is, I will be only enumerating the properties, that delta t is the same as delta minus t, which is obvious because it's only defined at the origin. If you fold the time axis, the point 0 still stays the same. Right? So this is one of the properties. Second property is that if you multiply any arbitrary signal x of t with delta t, it is actually the same thing as x of 0 into delta t, which is again quite obvious from the if you look at the description of this delta t, because it's only defined at t is equal to 0. So आपके x of t में जो भी आपका वेव फॉर्म है, जो भी आपके सिग्नल वैल्यूज है outside t is equal to 0, because of this they will vanish. So it's equivalent to x0 delta t. Similarly, if we shift our delta function, so if I have something like this, x of t into delta t minus t naught, so it will be x of t naught into delta t minus t naught. It kind of follows from this, because if you have a shifted delta function, so let this be t, there is some point t naught, it has been shifted to that point. Fine. Then if you have any arbitrary signal x of t, चाहे कुछ भी इसका value हो, when you kind of multiply them, only this point is what will remain, because everything else, it will vanish, it will be multiplied by 0, so it will be negated. Fine. So again, this property follows. Then there's a very important property which we will be using a lot. It is basically, it again follows from the definitions, from these two definitions, and it is like that if I have a signal x of t, you multiply it by delta t minus t naught, and then take the integral from minus infinity to plus infinity, it will result in x of t naught. And again, this is something which follows from this property. Fine. Because if you see x of t into delta t minus t naught, it is actually equivalent to this. Fine. And you can take x of t naught common, so it will be basically, if you integrate this, x of t naught will stay outside, and it will be integral of this thing only. But you know that integral of an impulse function, whether it is a normal impulse function or a shifted version, it is always equivalent to unity. So you will have x of t naught back. Fine. So it's a very important property of an impulse function, and we will be using all these properties when we actually use impulse function for characterizing our systems. Then there is another one, this probably we will be discussing when we discuss the systems, that if you have any arbitrary signal x of t, it can always be expressed in terms of the impulse function. Right? So x of t is any arbitrary signal, tau is a dummy variable, it represents time, right? So you have this signal x of tau, it's the same as x of t, just that it is a mathematical practice that we don't operate on the original variable, we always operate on the dummy variable. So it's x of tau multiplied by the shifted impulse by that amount of time, integrated over all the time axes with respect to the dummy variable. It's a very important result. We will be discussing this in chapter 2 when we discuss LTI systems. Fine. So this was all about impulse function. Again, I would like to repeat, in the discrete time domain, it is pretty straightforward. But the problem is in the continuous time domain, because in continuous time domain, we can't define a signal only at a single point. It has to span some time interval. To cover that, we basically introduce two mathematical criteria as a definitions that an impulse signal must satisfy. First, it should be equivalent to 0 for all the times except for the origin, and the area under this impulse should always be equivalent to unity. Then to graphically visualize it, we often express this impulse function as the limiting case of a gating function, a rectangular pulse gate function, such that the rectangular pulse, it has a width t and height 1 by t, and the time period t, it tends to 0. So I can say it is a width rectangular pulse of width 0 and height infinity, so that the area under this curve is always equivalent to unity. So it is basically approaching this thing. Then it has some properties like folding reflection property, it is the same. And if you multiply any signal with the unit impulse, you will get the signal only at that instant where the impulse is defined. And you can always express any arbitrary signal x of t in terms of an integral like this. We will be discussing this particular property. I will be at least using it in chapter 2. Fine. So this was a discussion about elementary signals that we will be using. Right? Additionally, we have one more, although we don't use it that often, in signal and systems, but just for the sake of completion, it is basically the ramp function. Right? So I will quickly write down how we express it. It is defined as r of t, and it has a value of t for t greater than equivalent to 0, like this, right? And just a second. And you can always, I'm sure you must have seen this signal a lot. So it is graphically shown as like this. This is t, this will be r of t, and this is the ramp. Fine. And you can have a similar kind of a definition in the discrete time domain, as r of t will be having a value of n for n greater than equivalent to 0, and 0 for n less than 0. So in that case, it will be only the sample. So this is n, this is r of n, like this. 0, 1, 2, 3, 4, 5, and so on. Right? Another thing that I must have said here, especially with respect to this, you can always express impulse signal in terms of unit impulse, unit step, जो इससे पहले हमने किया था. So like here it is only defined for one instant of time, so I can always express delta of n as a difference equation, u of n minus u of n minus 1, right? So I'm subtracting from the original unit step function another unit step function which has been shifted towards right by 1 unit. Again, you can easily see it graphically. आप यहाँ आराम से देख सकते हैं, जैसे हमने we had did an example like this. Similar way you can visualize this. Similarly, in the continuous time case, we have a relation that delta t is equivalent to d by dt of u of t. Discrete time domain, we have difference equation. In continuous time domain, we have the actual differential. Fine. So okay, this was all about the unit impulse function. It is a very important function, and we will be using this a lot.